What's up, everybody? Hi, Dr. G. I know you went over an example on office hours. I was wondering, for the exam, are we going to have to watch out for all the circuits if they have capacitors that don't do anything? I'm not sure what you mean by that. I mean, you can have capacitors that, if they bridge like two parallel lines, they don't add up to any more capacitance. I mean, that's true. Like if you have I don't know, some stuff happening here, or whatever. Yeah, something like that could be on the test. Yeah, for sure. Yeah, like this capacitor doesn't do anything because these are supposed to be at the same potential. Yeah. Ooh, all right. Let's see. How are we doing on set surveys so far? Here, let me start this off. Week 5, lecture 4. Nice. Week what? Week blank. Sorry. Week 5. I think this. Week 5. There we go. Last lecture of the second to last week. Pretty cool. But yeah, let's see. Where are we at? Ooh, 50%. Not bad. Getting close to 80. Getting close. So yeah, I think someone on Campus Wire was pretty good. They posted a screenshot of this and they posted the link. But yeah, if you haven't done your surveys yet, try to do them either today, tomorrow, over the weekend at least. I think the deadline is gonna be Tuesday morning that they're gonna close it off. So if this number gets to 80%, everyone in the class gets bonus points on the grade. So helps everyone. I don't curve this class, so helping out your friend doesn't hurt you. I hate that with classes that are heavily curved. You're less incentivized to like help out your fellow peers because you're like, oh, I don't want the curve to, you know, go up. I want the curve to, you know, I need to be ahead of the curve. Well, that's kind of a. I think it's a non-productive way of doing things. Because I mean, all work, all science is collaborative at some point, unless you're scooping each other on papers. And that's why sometimes, yeah, the world of academia can get kind of rough. Need 30% by Tuesday. Well, this just needs to go up to 80%. So 30% of the class. So I mean, we can calculate that, right? What would 80% of the class be? I can tell you like how many people are missing. They won't let me see who hasn't done it because it's all anonymous. So I can't like publicly shame people and say like, hey, do do your reviews or else. But see, there's 114, so 0.8 times 140. Wow, that's a big class size. I thought when I started, I'm pretty sure we were in the 90s. They just kept slamming people in this class. Okay. 91.2. So maybe they round up. So you need 91 people really to do it. So 91 minus 57. So another 34 students. 34 students are missing from the surveys. Grant close. The meat of the class to start. Is there anyone? While we are waiting for the meat of the class to start, is there anyone that hasn't taken the survey yet? Maybe take it right now. I agree. And actually, this is what I did during. It was my second to last lecture. Or, yeah, sorry, it was my last lecture. When I was teaching 5A last quarter. I would always usually have like a clicker question at the beginning of class that I would have the students spend 5 or 10 minutes on, and then the clicker question for the last day of class was just do the survey, please. Like, you're here, do the survey. The question was like, did you do the survey? And then I played the cello for them while they did it, because I would always play the Jeopardy music during clickers, which some people say is like the Kahoot music. You know this? Yeah, it doesn't. I would play this like during class. But some students say it's the Kahoot music. I'm like, no, it's not. So yeah, maybe wait. Today is like kind of the last day. Maybe on Monday, because Monday's like the absolute last like day you can do it. Maybe Monday, if we're not at 80%, I'll start bullying people and say, hey, if you're watching right now, you need to do the survey. Yeah, I would play cello for you guys while it happens, but my studio closet here isn't large enough. Can't really fit a cello in here. I can barely fit myself. Okay. All right, let's kick things off. Yes, so a couple news announcements. I'll put this in a Brew and Learn announcement later tonight. But midterm 2 is tomorrow. Same procedure as midterm 1. Opens at 12:30. Finish it by midnight. Try to use the attached supporting worksheet if you can. If you can try to like write directly on that digitally, whatever. I don't care. Makes life a little bit easier for partial credit. It's open notes, open book, open whatever. Just don't use AI. Don't copy paste AI. And I have noticed. Yeah, because I ran this test through AI just to see what happens, and it gets some of them wrong, which... The reason why that's happening is we're getting to more complicated visual things that AI can't really determine. Like, it can't really figure out. It's getting better. Like, AI's getting good. But there's certain things in physics it can't really get. In terms of, like, arranging circuits, for instance, or, like, seeing geometries of charges. So, yeah. Right. Submit your work to Gradescope. If you have any questions, email Albert during like normal business hours. Yeah, please don't email Albert at like 11 p.m. at night. He's also on East Coast time, so that's 3 hours ahead for him. So that'd be like 2 a.m. So try to be a little considerate when asking Albert for clarification or help. If he doesn't get back to you and it's late, you can email me, and I probably will respond because I'm a night owl and I'm usually up pretty late. So, right, all the homeworks are out, so you should be able to do all those. Last one's due on Wednesday. Try to get it done sooner than later. I still have people telling me that, like, oh, I need an extension because I screwed up my time zone. I'm like, dog, this is the last week of the course. We've had how many homeworks and you haven't figured out the time zones? Also, I give like a whole week to do the homework, so like, please just do it ahead of time. Don't wait until the time zone deadline to screw you. And yeah, you'll take the exam Friday. I will try to get it graded by Monday. No promises. It's pretty tough to do that, but at least by like Tuesday, because then what I want to do Wednesday after you submit your last homework is I'm going to get final grades into Brew and Learn. And so at that point, you'll be able to see everything that you've done, and you'll have a pretty good idea, hopefully by end of Wednesday, early Thursday, where you are before taking the final. And then the final will be on Friday. I'll announce more things about the final after the weekend. Just focus on exam 2 for now. What else? What else? Yeah, I think that's it. Yes, regrades for partial credit will be the same process. Once I get them out to you, although the window is going to be probably closer. Last midterm, I gave people like almost 5 days to submit regrade requests. I'm probably going to shorten it to like 2 or 3 days, just so I can make sure I get final grades in by the deadline. So whenever I release grades, try to go through your exam. I'll make an announcement about this, but go through your exam within the next 24, 36 hours and try to like write up your regrade thing so that we can do that. And then for the final, I got to see what the deadline is between you taking the test and me submitting final grades. They'll give me an announcement on Brew and Learn when that happens. And that will determine if I can do regrade requests for the final. It just depends on the timing. If they want final things by Monday, like, I just can't. Some of y'all were asking, like, can we get a practice test? And I'm already, like, slammed trying to get too many things done in, like, a week. Drafting another exam that, if it isn't exactly like the midterm, people are going to get mad at me. Yeah, it's kind of an effort, so. Okay. But today, we're going to go over Kirchhoff's, or Kirchhoff, however you pronounce it. I like Kirchhoff. Someone's going to get mad at me and say this wrong. But we're going to go over the loop laws and the juncture laws, and these are really critical, important things for being able to solve complex circuits, especially circuits when you have like multiple EMF sources or multiple batteries. So when you have batteries in like different places, it kind of makes things weird to try to calculate just V equals IR. So we can instead use Kirchhoff's laws to do that. And it makes life easier. It's nice. Okay. Let's pull it up. Battery 10. Kirchhoff's. They call them his rules? They're not laws? Wait, what? Are they laws or rules? What's the difference? Are they theorems or axioms? I thought it was Kirchhoff's laws, but okay. Okay, so here are the two rules, and then we're going to go over, like, don't worry, we're going to do an example and explain what this means, because there's a lot of kind of finicky details you got to remember. So the first rule is what's called the junction rule, and that states that the sum of all currents entering a junction must equal the sum of all currents leaving the junction. So here, let me actually, like, here, we're just going to do them one at a time. And the reason why we're doing this is, say, for instance, you were asked to try to determine what the current and resistance and voltage is on this. Here, because you have like battery sources here and here, and the resistors are in all sorts of weird areas, this is like very difficult, if not impossible, to reduce to a basic circuit. And when we talk about basic circuit, right, that's when you have like a single voltage source and then a single effective resistor, right? This is like some V naught, and then this is like R effective. This is the ideal basic circuit. Because you got like voltage sources here, and then like these are in series, but then like this is in series with this, but it's in parallel with another voltage source. And then this is in series with this. Like, it just gets really complicated. So we can't do this. And that's why we need to use Kirchhoff's rules. But using Kirchhoff's rules, it is possible. So, yeah, the first rule is called the junction rule. And it says the currents entering in a junction has to equal the sum of the currents exiting a junction. So what we mean by that is that let's say you have... And a junction is where, like, wires meet. Okay, so let's say we have something like this, for instance. Okay. And this is the juncture. And then let's say... Here, let me make the juncture, like, blue. And so this, for instance, let's say like you have some current that you know is coming into here, but then it's splitting out with like another current here, I2, and then it's splitting out to another current here, I3. In this case, by the junction rule, what we would say is that I1, that's the sum of the currents going in, is equal to I2 plus I3. Okay? So anytime you have currents that are meeting at a certain point, you can always relate them using this. And this is kind of similar to conservation of energy, right? You know, energy in has equal energy out. You can't just start losing energy just because you're splitting it. So this is kind of where this comes from. The second rule is a little bit more complicated, and that deals with the loop rule. Oh, here. Oh, they do have a graphic of it. Okay, but this is like nuts. Like no one would ever do this. This is what they say. This is the example they give. Dog, what? That's like ugly. This will never happen. We're not going to do this. But I guess, yes, if you had this happening, this looks like that one intersection in Beverly Hills. Y'all know what I'm talking about? It's like the 6-way stop sign. But like everyone... It's always kind of a you just really hope for the best and you just drive out to it. Yeah, right. Amelia's like, yes, I know exactly where this thing is. Yeah, this is what this is. It sucks. Yeah, bro. It's always like the biggest game of chicken. Just like I'm just gonna go and no one's gonna hit me. Okay. The next one we have is the loop rule. Okay. Loop rule is really cool. And it says that the algebraic sum of changes in a potential around any closed path or loop must be equal to 0. Okay, so this just looks like really like fancy nonsense. Okay. But basically, well, here, let me do the simple example of what this would be. Let's say, for instance, you have a circuit here, and let's say this is V0, right? And then let's have it go across like 2 resistors. It's just like pew, pew, pew. Then like another resistor. And then because this is a very basic circuit, right? There's a single current going all the way around. And for things in series, they have the same current, right? So the I1 here is the same as the I1 here, which is same as the I1 here, right? Because we know things in series have the same current. And then let's say this has a resistance R1 and this has a resistance R2. So sum of voltages, and again, I always like to start at the positive end and call this like V0 and then call this like 0. Means that if you go around, that as you add up all the voltages, you should eventually get to 0. And so what a lot of people do is they'll start at the 0 point here and they'll go across. So here's the rule. If you have a battery like this and you move, if you move this way, that equals positive voltage. If you move this way, that equals negative voltage. Okay, if this is some V0. And what I mean move is when you're creating loops, you kind of like stick your pen down and you just start like tracing where you go, okay? So as you go along here, let's say we start here. you're going to gain that change in voltage, summing the voltage, that's equal to a positive V naught. So you would start here, and that would give you V naught. Okay. And then we need to talk about like what happens as you keep going across things. So we're going to keep going this way, right? And then we're going to go across a resistor. Okay. Now here's the rule for resistors. If you have a resistor like this and you're defining the current to be in this direction, let's say this is the current. Let's say this is like I0, and then this is a resistance R0. If you move across the resistor in the same direction as the current arrow you drew, so if you move this way, this is equal to negative I naught R naught. This is called a voltage drop. You drop voltage as you move across resistors in the same direction as the current is flowing. Okay. So this is like, so if you move across, I would say like you move against. And then this is like move with I naught. But if you move the other way, move against I naught, then this is equal to positive I naught R naught. Okay. So here, let's organize this a little bit. So here, we'll call this like how to add all these things. Yeah. Okay. So, and here, let's move this down. We start here. And that's going to be a positive V naught going from here to here. Then we keep going and we go across this resistor. Notice that we're going in the same direction as the current. So that's going to be minus R1, minus I1 R1. Okay, so this is going to be minus I1 R1. Again, this is plus V naught. And then we're going to keep going, right? We're going to keep going across. Again, we're going across this resistor in the same direction as the current. So that's going to end up being minus R2 minus I1 R2. I just want to know. There you go. And this is minus I1 R2. And then the sum of all this has to be equal to 0, right? So this is the sum of the voltages. Okay. So then you get something pretty cool here, right? So now we have an equation, right? V naught is equal to, notice how I can like factor out the I1. Or, so I'm going to say V naught minus I1 R1 plus R2 is equal to 0. Or, right, V is equal to I1 R1 plus R2. Do you see how this also agrees with the very simple, like, Ohm's law? Where if we had just a simple battery V naught, and then we combined these two resistors, that would just be a super resistor R12. And you would get the same thing here, right? Like V naught is equal to I12 R12. But I12, right, is the same current through this and this. So it's the same thing as I1. So you would get the same thing. V naught equals I1. And then this is R1 plus R2. Look at that. Physics is real. It's not a lie. Okay. Does that make sense so far? Very simple circuit, how we're doing it. These are the rules you have to know. And then we're going to use these rules to make like really complicated circuits and solve for stuff. Wow. Well, I got a really complicated one here. Okay, cool. Can I have it like without the loops? Bum 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 bum. Yeah, just need more practice. Totally. I totally get that. I want to find like a good one that has. I don't want all the loops like already written for me though. It's like kind of cheating. Let me just get one real quick. Hold please. Hello, I'm from India. Hello, I'm from Los Angeles. Ion, what's up? Let me see. Kirchhoff loop law question. I want like a fun one. This one's pretty fun. But I want one with the answers too. Okay, we can do this one. It's not too bad. And then we'll do like kind of a more complicated one. See how this works. Because eventually at some point you start needing calculators and it becomes like pretty intense linear algebra, but I'll show you some tricks on the calculator that you can use to solve it. All right. Let's say, for instance, I want to solve for all the currents and voltages across these resistors. Let's say my goal here is to figure out I1, I2, and then V1 and V2. I'm trying to analyze like how much. Let's say I'm trying to figure out how much power is being dissipated in each resistor, right? I know power is equal to I times V. So if I can find the current and the voltage of one of these each of these resistors, I can figure out the power dissipated in each. And then you can actually figure out the power dissipated in the whole system, which is pretty cool. Okay, so the first thing I'm going to do is I'm going to like try to you always want to define what your currents are, okay? So in this case, this is going to have some current here. So I'm going to end up calling this like I1. Okay. But then there's a juncture here. Okay. So I can't continue to call this I1 because there's also probably current from here that's going to contribute. So we're going to stop with just calling that I1. And then we're going to define this, the current coming down here. Ooh, I see how they're both called 1. Here, let me call this I0. Just for funsies. I'm going to call this I0. I'm going to call this I1. And then whatever current's flowing here is the same as the current here. So this is also going to be I0. This may be an unnecessary step, but sometimes there's a resistor here, and you would need this. There's a resistor after that junction. Exactly, right, yeah. So you can't just, like, continue on here. This is a junction. Anytime there's junctions, you got to be careful. Because there is going to be, right, some current here, I2, which is the same as this is going to be I2. Okay, cool. So we've defined our currents, right? So we have I0, I2, and then we have I1 here. The next thing we can do is start to write our loop laws. Okay, so let's write our loop law for this one first. Okay, so we're going to call this loop A. Let's call this loop A. Okay, but actually, let me use a different color for it. I remember this one being like kind of a simple example, but I just want to show how it works, and then we're going to get harder. Okay, so this is A. So going around this way. Okay, loop A. If we start here, for instance, and go across the battery, we're going from the negative terminal to the positive terminal, right? So if you're going from the negative terminal to the positive, that's going to get us a starting 1.5 volts. Just to be clarified, we can write the current coming back to V1 as I0 because of the loop law. Well, yes, because whatever current is flowing here has to be the same current flowing here. On either side of the battery. You can't have different current. So, but you can't say that here it's I0 because you have I1 pushing this way and then you have I2 in this. So this current actually ends up equaling the sum of this one and this one. Why can't we go down until the beginning of R1? It's the same wire. Because there's a juncture. Here's the issue. When we get to this point here, it's also meeting this current coming in. So this doesn't get to just ignore it. So there is a juncture there. Anytime you have currents that are meeting, you have to like start a new current. And then use the juncture laws. Which I don't think actually we need the juncture law for this one. If there was a resistor here, we would. And that'll be a harder example to show. But for now, write the loop law. Yeah. Resistors, yeah. Again, it's really weird that we teach capacitors before resistors. Resistors are kind of like the basic thing. But okay, so we gained 1.5 volts going across the battery. Then we come across the resistor. Notice that we're moving, right, in the same direction as the current. So that's going to be minus I1 R1, which R1 is 100. So we can say minus I1 times 100. Or here, I'll leave it as R1. Okay, and then we come back. And then this would just be equal to 0. Pretty easy, right? You can actually determine I1 right away from this, right? Because this is a known variable. You already know this. You're good. But let's show how we would write it also for loop B, all right? And for loop B, we're going to go this way. This is loop B. So again, I'm going to start here, which means I'm going to go across 9 volts, right? I'm going to come around. I'm going to then, notice I'm still going in the same direction as the current I defined. So this is going to be minus I1 R1. And then as we come back, I'm now going to go across minus I2 R2. Aeon, did you already get it? Let's see. Well, we'll see if you're right. Okay, equals to 0. Okay, so now we have two equations, and we have two unknowns. This is the key thing, and this is a systems of equations. So the number of unknowns has to be less than or equal to the number of equations. So we have two unknowns. We have two equations. We're good. Okay. So now you can start plugging some values in. So I have 1.5 minus 100 I1 equals 0. And then I have 9 minus 100 I1 minus 200 I2 is equal to 0. We can get I1 right away from this, right? This is easy. I just move it over, divide by 100, and you get, right, from this, you get that I1 is equal to 0.015 amps, right? Divide by 2, right? Yeah, cool. Now that you know I1 is equal to 0.015 amps, you can then plug that into here, right? Solve for I2. So that's going to get me 9. Notice that this is the same thing as this. So it's literally just 1.5. This is very easy linear algebra. It's going to get harder. I'll show you. So minus 200 I2 is equal to 0. So then, what does that get you? 7.5 is equal to 200 I2. So then I2 is equal to probably what you said there, Ayan. 7.5 divided by 200. That's equal to 0.0375. Oh, so a little bit different. You got 52.5 though, right? Did I do something wrong here? I don't think so. So I2 should be 0.0375 amps. Let me check. That is, I have the answer for this one. Yeah, it's 0.0375. Cool. Okay, so that's I2. And cool. So 15 milliamps. So 0.015. 0.0375. Move these over. And now you can solve for the voltage, right, for each thing, because V is equal to IR, right? V is equal to IR. So V1 is equal to I1R1. And in that case, right, that equals 1.5 volts. And then this will end up equaling, what is that, 200? This is a very easy one with algebra. 7.5 volts. Cool. Nice. Okay. So that's how to use the loop laws. Notice we didn't have to use the juncture law at all. Oh, also you could, well, if you wanted to solve for I0, if you wanted to solve for the current through the battery, that would be that I0 plus I2 is equal to I1, right? Current in is equal to current out. And so you get I0 is equal to I1, which was 0.015 minus 0.0375. Oh, wow. So the current runs in the other direction. That's actually kind of cool. So this equals, yeah, 0.015 minus 0.0375, which is going to be minus 0.0225. Where is V2? So, yeah, sorry, V2. I'm referring to the resistant, the V2 of the resistor, not this V2. Yeah, they shouldn't have called this V2. Okay, here, this is V2 of the resistor. Yeah, my bad. Sorry. V1 of the resistor. Or, I don't know, V resistor 1. V resistor 2. Yeah. Okay, there we go. So interesting here. You get that I0 is equal to negative 0.0225. And when you get that, that's not a mistake. You can have negative currents. What that tells us is the sign convention we came up with for defining positive current going this way is wrong, because the current, the value of that current is actually negative. So in reality, current is not flowing this way for the battery. It's actually flowing this way at 0.0225 amps. And the reason for that, right, is this 9-volt battery is much more powerful than the 1.5. So this voltage that's coming from here is actually pushing through this juncture and actually reversing through the battery. But it's cool. That's as long as you keep. This is the same thing, right, in kinematics, where we define like up as positive, down as negative. But you can switch that, right, if you're using pulleys. As long as you're consistent with your sign convention, if you get negatives, it just means things are running in the other direction. Ayan, what'd you do wrong? Did you, because you got the first answer correct, but you got the second one wrong. So this is how we can find if the capacitor doesn't contribute to overall equivalent capacitance better than with the other material. Not quite. I don't think we use Kirchhoff stuff for capacitors. Or I don't think we'll use them here, because no current technically flows across a capacitor. That makes sense. we will mainly use this for batteries and resistors. I don't think I'm going to make you use Kirchhoff with capacitors. No, it's okay. Okay, let's see if there's a more fun one we can do. I want one that's gonna like hurt. I want one where I'm gonna have to do. Well, here, actually, there's a clicker question we can do real quick, and then we'll get into some pain. Okay, clicker. Okay, it says which of the following is not an accurate expression of Kirchhoff's sum rule for the following circuit done below. This one looks really interesting. Maybe we should solve this one. Is this also on your homework? I wonder if this is on your homework. I mean, I'm fine doing like one of your homework questions. I just want something where I have the answers. Because I always like to get some satisfaction of like, look guys, it's real. I'm not just like making shit up. You sometimes have professors that do that, right? They just start doing questions on the board, and then they get to the answer, like, and that's the answer. And then you end up finding out they were wrong. Oh, it's the worst. I don't know. Okay, so let's look here. Which of the following is not an accurate expression? Sadist professor. Yeah, I'm trying to. I want some. This is fun. Well, I want it to be painful because I want to show you how the calculator makes it so much easier. Holy circuit. This is a nasty circuit for sure. You got two batteries in different parallel lines. You got resistors fucking everywhere. What's going on? Luckily, they did label the current. They labeled everything for us, which is nice, right? Look, they labeled I2 is this way. They called this one I1. Notice, right? This I1 is different than the I2 here because you're at a juncture, right? I2 doesn't keep going. Then they labeled this as being I3. This is I5, which is different than this, which is I4. They didn't label this current. Although I don't think you need to, because there's nothing in between these two. I think technically you can bring these junctures like together, if that makes sense. So you could really actually just get rid of this. And like squeeze it like a triangle. And then it would just be like I2. Oh man, that would be a four-way intersection though, right? Yeah. Wow. Yeah, okay. Anyways, let's see here. So let's see where they're making some mistakes. Okay, first one. Is this correct? So they're starting at V1, starting here. They're going across. Cool, that's positive. Then they come this way. They're going in the same direction as what we called I1. So that's minus I1 R1. And then they're going across I2 R2. This is correct. Yeah, this is okay. This is a decent loop. This is an okay loop. For B, so we're going across V1 positive. Okay, look, they're coming way over here. Now they're going across the backwards way of a voltage source. When you go across the voltage terminals in the opposite direction, right? So remember here, this is like negative, this is positive. If you go against what the terminals are, you have to subtract voltage. And that is what they're doing here. You see how they're subtracting V2? So this is the big thing. They're going this way. So this is subtracting V2. Then you still subtract I3 R3 because you're going in the same direction as I3 and R3. And then they subtract I2 R2. This is also correct. Wow. That's a cool loop. That's a really cool loop. I like that one as well. Okay, let's see for V2. Oh, so they just have V2 I4 R4. Well, that's just doing this one, right? V2, you come across. This is I4 R4. That one's also correct. I1 plus I2 plus I3 is equal to 0. Ooh, no. Because that's this juncture. So current in, which is I1 plus I3, would have to equal current out, which is I2. And that's not what this says. So this one is wrong, but that's the correct answer choice because they said which one is not correct. And then let's see this other one. V1 minus I4R4. Okay, minus I3R3 minus I2R2. This is also correct. Yeah, cool. Notice, right? When they came across this thing, they went in the same direction as the current. So that's why it's a minus I4R4. And then as you're coming this way, you're still going across the same direction as you defined I3. So this is minus I3R3. And then you're going across the same direction you defined I2. So this is minus I2R2. Cool. Answer choice there is D. Nice. Okay. Cool. We just had one clicker question on this one because I don't know. These are kind of lengthy problems to really do, and I didn't want to smash you guys down with too many things. Let me see in your homework if there's one that has like a cool circuit that I can do. I can just show you how it works. Homeworks. Sec. Oh, Jesus. Oh, man. Yeah, that's a mean one. That's also a mean one. Yeah, fuck it. Let's go for some pain. But that only has one unknown. Alright, we're gonna do this one. Okay, yeah. Let's do this. I like this. We're just going to solve all the things for this. Okay. Let's do this one. This is a good circuit. I was also tempted by this one. But they're only having you solve for one thing. Everything else is given. So this isn't as cool with the algebra that I want to show you. This is just like one unknown thing. I'm pretty sure you can figure this out pretty easily. What would be difficult would be if they just gave the voltages and the resistances, and then they had you solve for all the currents. That would be cool. That might be like a final exam question. But here, let's do, this is like medium level. This isn't like super hard, but it's not super easy. Okay, let's start defining. So the first thing you do, when you see one of these questions, you want to start defining directions for all your currents. Okay? Sibley sad face. Oh no. Uh-oh. No, don't worry, don't worry. It'll be fine. Okay, so I'm going to define this current to be I2. And notice that that current is going to be the same going across this battery, right? We're not introducing any more junctions. We're not introducing any more, whatever stuff happening. Everyone's like, no, don't do it. Okay. So here you also have I2. And then here you're also going to have I2. All right. Now let's talk about what's going on here. All right, I see positive to negative, so I think I want to define this as I3. So notice, right, I3 is like doing this, and that means this is also I3. Okay, cool. So then what's left is this, and we're going to define that as I1. Okay? So far we've come up with all the directions of our different currents. And you want to make sure stuff is consistent, right? Don't like draw this going this way and this like going this way because they're on the same loop. Things in series, usually have current running in the same direction. Unless they run into a juncture. Then things can flip. Okay. So let's write out loop A first. Let's call this like loop A. Let's call this loop A. Okay. We're going to go, maybe like draw a little picture like this way. This is loop A. We're going to start here. So I'm going to go across V1. So that's going to be V1. So here, loop A. That's going to be V1. Nothing's happening. Nothing's happening. Oop. Now I'm dropping minus I1R1. And then we drop here minus I2R2. Because again, we're moving in the same direction as the currents that I defined. Okay. And then this has to be equal to 0. Now let's look at loop B. Let's call this B. So let's start here. And so that's going to be V2. Keep going across. Not hitting anything, not hitting anything. Oops. Minus I1R1. And then we're going to keep going. And then we're going to drop minus I3R3. And then this is equal to 0. So this is loop B. Okay. So far, I have 2 equations. But let's think about, like, how many things are unknown? Well, I don't know I2. I don't know I3. And I don't know I1. So that's 3 things I don't know. So we have 3 unknowns so far. Which is I1, I2, and I3. And if we don't know I1 and I2 and I3, then I need at least 3 equations. I only have 2 so far. So, there are 2 ways we can do this. We can either create another loop, which I could call like a super loop, or we could create a juncture rule. Ion, you think you got it already, dude? Okay, let's see, dude. I'm gonna use a juncture, and let's come up with a color. We're gonna say juncture, and we're gonna call this like juncture C. Okay, this is juncture C. And what I see for juncture C, right, is that current coming in, so I1 is equal to current going out of that juncture, which is going to be I2 plus I3. Okay. So now I have 3 equations that we can write out. So we got V1 minus I1 R1 minus I2 R2 is equal to 0. We got V2 minus I1 R1 minus I3 R3 is equal to 0. And then we also have that, let's move this all over to the side. I have I1 minus I2 minus I3 is equal to 0. So what we could do, this is a systems of equations, right? This is a system. But it's a 3-variable system of equations, right? So what I would have to do is I'd have to sub in this for I1, and I have to sub in here for I1, and then I'd have to do some other substitution between these two to then cancel out and eventually get like either I2 or I3. That's kind of messy, and honestly, it sucks. I wonder how much time do I got? I got 20 minutes. If I show you the hard way, you'll probably have an appreciation for the easy way. Maybe, yeah, let's do the hard way. Let's be difficult. And then literally doing this the easy way takes like 2 minutes. And you'll be like, oh wow, yeah, let me do the easy way from now on. So let's take yeah, we're gonna do this. This is just algebra at this point. We're just gonna do. Okay, so solving algebraically. And then we're going to show you how you can solve it using linear algebra, which is super nice. And then where are the values for this? Okay, so R1 is equal to 2. Oh, and it's times 10 to the 3. Okay. All right, 2,000. R2 is equal to 1,000. R3 is equal to 1,000. All right. Let's take this and plug it into here, and let's plug it in to here. Okay? So now what we're going to have is that V1 minus I2 plus I3 R1 minus I2 R2 is equal to 0. And then for this one, you're going to get V2 minus I2 plus I3 R1 minus I3 R3 is equal to 0. Okay. I think I want to do like elimination method here. Oop, lost my thing. So to do the elimination method, I want to get my unknowns kind of like lined up. So I'm going to move all this stuff over, and then, well, I'm just going to flip it. I'm going to like move this over, then multiply everything by a negative. So we're going to get that like I2 R1 plus I3 R1 minus, so plus I2 R2 is equal to V1. And then that I2 R1 plus I3 R1. A junction is a node, correct? Yes. Is equal to V2. So all I did, guys, is I moved this over by subtracting it, and then I multiplied everything by -1. So that's why these all became positive, and that's positive. Okay. Let's group. So okay, so this is, now we group. So I'm going to get R1 plus R2, I2, plus R1, I3 is equal to V1. And then here, grouping by I2, I'm just going to get, okay, R1, I2, plus R1 plus R3, I3 is equal to V2. Okay. Well, I should have done this. Sorry. Let me get rid of this one. Okay. So let's plug some values in. R1 and so R2 and R3 are the same. But I'm never adding R2 and R3. Sorry. Let me bring this down so I can see it. Okay. So R1 plus R2, so that's 3K. So I have 3,000 I2 plus 2,000 I3 is equal to whatever V1 is. And then I have 2,000 I2 plus 3,000 I3 is equal to V2. So let's multiply 1 by 2, 1 by 3, right? So let's multiply this by -2, and let's multiply this by 3. So then I get -6,000 I2 minus 4,000 I3 equals -2 V1. This is 6,000 I2 plus 9,000 I3 is equal to 3 V2. And now this is the elimination method. You may remember this from like high school. This, you just add these two. This cancels. You get 0. And then this is going to get you 5,000 I3 is equal to -2 V1 plus 3 V2. All right. So now we can plug in some values, right? So I3 is equal to -2 times 1.6. That was V1. Plus 3 times 1.4. And then all over 5,000. Where's my calculator? When's office hours? Not today. Next one's on Monday. And then plus 3 times 1.4 is that. And then we divide this by 5,000. Oh, wow. That actually came out to be a nice number. It's kind of cool. So, I3 is equal to 2 times 10 to the minus 4. Cool. Now you can use that to figure out I2, right? Because you can just back substitute this in. So now you can like plug that back into here, right? So now we have negative 6,000 I2 minus 4,000 times 2 times 10 to the minus 4 is equal to negative 2 times 1.6. And let's see what we get. So negative 2 times 1.6 is equal to that. And then I'm going to do plus 4,000 times 2e to the minus 4. I get that, and then I'm going to divide this by negative 6,000. And that gets me 4e to the 4. Okay. So I get I3 is equal to 4 times 10 to the minus 4. Cool. All right. I like that. And then the last part we had was from this, right? I1 is equal to I2 plus I3. So I1 is equal to I2 plus I3. And so that's going to equal to 6 times 10 to the minus 4 amps. Okay. So, yeah, that's the manual hard way to do it. Is get your systems of equations, and then you have to go down this little rat race of, like, solving for it. Okay, but let me show you, like, the easy way. Right? Where's my select tool? Okay. Easy way. You still have to rearrange a little bit, okay? But life is a little bit... You don't have to do as much of the substitution stuff. I'll show you why. So, the goal is to get our equation in this form. I want, like, something I1 plus something I2 plus something I3 is equal to a number. So this can be equal to, like, whatever. Okay? This is the goal. Here, goal. It's good to have goals in life, right? Goal. So let's rearrange everything so that it looks like that. So with the blue one, right? That would be negative R1 I1 minus and actually here, let's just multiply, let me just like put this over, multiply everything by negative 1, just to make life easier. Okay, this is R1 I1 plus R2 I2 plus 0 I3 is equal to V1. For this one, it's going to be R1 I1 plus 0 I2 plus R3 I3 is equal to V2. And then for the last one here, it's going to be just... they're kind of the same thing. The dielectric constant, I think, refers to, like, vacuum. So this is I1, and then this is plus negative 1 I2 plus negative 1 I3. And then this is equal to 0. Right? Okay. So, using our numbers, okay, I'm just going to look at, like, what the coefficients would have been. I'm just going to write out the coefficients, and I'll show you why we do this. That's going to get me 1,000, right? 2,000, another 1,000, sorry. 0, and then 1.6. The next column is going to get me 1,000, 0. Or wait, sorry, R1 is a 2,000, not 1,000. Let's fix that. 2,000, 2,000, 0. R3 is 1,000. And then this is going to be 1.4. And then the final one we have is 1, -1, -1, 0. Okay. This right here is called an augmented matrix. This is an augmented matrix. Where technically what they do is they define it as like a 3 by 3. So this is like a 3 by 3. And then these are like is equal to like your answers. Okay. The real way to do this with like linear algebra is to thanks sensation, I do need a drink. Is to take this 3 by 3, figure out the inverse of it, and then multiply both sides. But there's an even easier way to do it, which is called row reduced echelon form. Which, if you've taken a linear algebra class, you've learned how to do this by hand. But I'm going to show you how to do it on the calculator. And so this is a great way to solve any sort of systems equation. Even if you just have a TI-84. Doesn't have to be the gold edition. It can be whatever edition, you know. Anything that, I think even an 83 will solve it. But, okay, what you're going to go is you're going to go to, where is it? Okay, second matrix. You're going to go to edit. And then, you haven't taken it yet? That's okay. Well, I'm going to show you how this works. You're going to create a matrix. In this case, it's going to be a 3 by 4. So you have 3 equations, and then the 4th dimension is like the answers. And I'm just going to plug the values in here. So watch. 2,000, 1,000, 0, 1.6. Next row. 2,000. Wake up, Neo. 1,000. 1.4. The matrix does have you, dude, here. All right, this is 1, -1. Follow the white rabbit, dude. -1. 0. Okay, cool. Second quit. Then what you're going to do is you're going to go to second matrix. You're going to go over here to math. You're going to go all the way down to the bottom where it says RREF. You're going to basically tell the calculator to do row reduced echelon form on this matrix. And then you have to tell it what matrix you're doing. So you go second matrix, and then this new matrix you created, matrix A, is here. So you just have it as an argument. Hit enter, and bada bing. Look at that. And here we can actually just show like what the matrix would have been. Oh, it actually doesn't show the whole thing. Oh, because it's too big. But okay, yeah. So there you go. So this is actually really cool. So, hey, forget about... I love The Sopranos. It's a great TV show. Okay, so here's the cool thing. So this right here, this is matrix A. So look what you got now. You got 1006E minus 4. Remember, right, when we were doing this, that this column referred to the I1 stuff, okay? So this is the same thing as saying 1I1 plus 0I2 plus 0I3 is equal to 6 times 10 to the minus 4. And then this is saying 0I1 plus 1I2 plus 0I3 is equal to 4 times 10 to the minus 4. And this is saying that 0I1 plus 0I2, right? 0, 0, plus 1I3 is equal to 2 times 10 to the minus 4. Yeah, RREF by hand is kind of like messy. But look at this, right? 1I1 plus 0 plus 0. This is basically saying that this is equal to I1. This is equal to I2, right? That's the only thing that isn't dying. And then this is equal to I3, which these are the exact same results we got for here, right? I1 was 6, I2... sorry, I wrote this down wrong, sorry. This is I2. I2 was 4, I3... I2 was 4, I3 was 2. Is that what we got? Yeah, look, I3 is 2, I2 is 4, I1 is 6. Yeah. And so that's the super easy way to do it. Anyways. Okay. Cool. All right. That's it for today. I don't want to go into another whole other section, especially when you got your exam tomorrow. So I hope that was cool, made some sense. You guys learned some stuff. Use that RREF trick in all your other classes. Anytime you have big systems of equations, knowing how to do that with your calculator is invaluable. It'll help you out so much. So I hope that's a skill you can take with you to other classes. But anyways, we don't have class tomorrow, so don't show up to YouTube or anything. You just have your exam. Focus on your exam. Get it done. And if you have any questions about things, email Albert. If he doesn't respond within a couple hours, you can send an email or DM to me, and I'll take care of it as well. And then, yeah, please wait until, like, Monday to discuss anything about the exam, like, on Campus Wire. I'm happy to explain stuff, like, once I have all the exams in. I just know for sure I'm going to have someone with, I don't know, their flight got delayed or something. I'm going to have to extend them till Saturday, so don't say anything until Monday. Cool. Indians Learn Physics, that's cool, man. Yeah, check out our channel, Ion. We do math and science stuff. This is a physics class I teach, but check it out throughout the week. Sensation can point you in the right direction. Okay, cool. Enjoy the rest of the week. Enjoy the weekend. Good luck on your test. I will see you guys on Monday. Peace.